Suppose we take a cube and we rotate it about an axis that cuts through two opposite vertices. What is the volume of the solid that it generates? This is a really fascinating problem, and it can be approached by breaking it down into two parts. First, understanding the solid generated at the top and the bottom, calculate its volume. And the second part, understanding the solid in the middle, which is really cool looking, and also calculating its volume. Now the first part is definitely quite approachable, so why not let's take a look at how to tackle the first part. Now, in order to tackle the first part, I'm going to set up a coordinate system because that will give me concrete things to work with in order to find the volume. So I'm going to put a unit cube as follows, with one of the vertices at the origin and the other vertices are at the points shown. In this case, then the axis of rotation will be the line x equals y equals z, which passes through 0, 0, 0 and 1, 1, 1. Now, how do we think about this upper part? Well, to give some intuition, first consider looking from the top, from the perspective of G. Intuitively, if we think about it, the cube starts moving away from the axis as we go from G to H, G to F, and G to C. And it looks like these are the furthest points away from the axis. And similarly, intuitively, if we look from the bottom, A is on the axis, and as we move from A to E, A to B, and A to D, it looks like the cube is spreading away from the axis and then reaches the furthest point away from the axis. Now, of course, all these are just speculation and I haven't proven anything definitive yet, but it suggests that we should probably look at the triangle BDE. So, this blue triangle here can represent a plane which slices the cube. And what is the equation of this plane covered by the blue triangle? It's actually quite easy to derive that because your coordinates of B is 0, 0, 1, or rather 1, 0, 0. Coordinate of E is 0, 0, 1, and coordinate of D is 0, 1, 0. So it's very easy to check that the equation for the blue plane is x plus y plus z equals to 1. Now, if you put it into this form, then it is evident that the blue plane is actually orthogonal to our rotation axis. So this is very useful because it means that if I use the blue plane to slice the cube into two pieces, I can separately consider the part below the blue plane and the part above the blue plane, and the two solids will not interfere with each other. So what I'm going to claim now is that the part below the blue plane will end up giving this shape here. Remember, the two parts won't interfere with each other, so we are permitted to analyze them separately. Okay, so now let us understand the solid below the blue plane better. And in order to do this, the first thing we observe is that we do have an equilateral triangle B, D, and E over here. So it seems useful to view from the perspective of A. So when viewed from the perspective of A, remember the rotation axis is orthogonal to the blue plane. So we do have our equilateral triangle very nicely presented here, and the axis pierces this diagram orthogonally to the screen. Okay, so moreover, by considering the symmetry of the situation, you can see that, or rather it's not difficult to deduce that the plane, the axis actually pierces the triangle at its centroid. So if we were to rotate this triangle around about the axis, what we'll do is we'll actually end up generating a circle. And since the three lines over here are straight lines, we are going to have a circular cone if we rotate this 3D figure around. So let's find the volume of this cone, which is also not difficult. So as mentioned, the equilateral triangle is over here, and the side length is quite easy to calculate. It's just square root 2. And so we have this over here, which means you can find the area of the base. So let's find the radius of the base. The radius itself is given by the height of the equilateral triangle times 2/3 the way, because the centroid is 2/3 the way of the height. So if we take the usual height of an equilateral triangle that has side length 1, scale it by our side length over here, square root 2, then times 2/3, we do get square root of 2/3 as the radius of the base. So the circle has area pi r square, where r is this. Okay, but to find the volume of the cone, we still need the height of the cone. So to do this, we going to find the coordinate of the centroid, which is where the axis pierces the blue triangle. So this is also quite easy to find out because we have the equation of the blue plane, and the equation of the rotation axis is x equals y equals z. So the solution to x equals y equals z and this equation is each of them is 1/3. So the axis pierces the blue plane at 1/3, 1/3, 1/3. And of course, the tip of the cone, which is A, is at the origin. So with the coordinates 0, 0, 0 and 1/3, 1/3, 1/3, we can find the height of the cone, which is 1 over square root 3. Now, by the way, if you didn't believe me earlier that the point of the pierce is the centroid of the triangle, you can check it now by taking this coordinate for the piercing point and check its distance to the coordinates of the side of the equilateral triangle. So anyway, now that we have the radius and the height, we can actually find the volume of the cone now, which is 1/3 pi r squared times the height. So plugging in all the values, we get 2 pi over 9 square root 3. Now this looks slightly ugly, but don't worry, at the end the result is actually something really pretty. So stay with me till the end to see the final volume. So just to recap, what we have here is we draw the blue triangle, we'll slice orthogonally to the axis, and we get a cone of this volume. Now similarly, if we look at this purple triangle spanned by C, H, and F, then again it's going to be orthogonal, and we are permitted to then slice and analyze this volume independently. And of course, by the exact same argument, we'll get volume equals 2 pi over 9 square root 3. So we have conquered the first part, and now we have to look at this very cool looking piece in the middle. So it's going to be a bit more difficult. It will involve a bit of calculus and vector geometry, but it's definitely something approachable, and you will definitely love to see the techniques involved. So let's now take a look at this middle part. But before directly calculating the volume, I would like to explore a scenario. So if we look at this scenario over here, what we have is we have a line segment at the point x equals to r. Of course, in this diagram, my r is 1, but in general, I'm going to let it be r. Y equals 0. So this in general gives a vertical line cutting through the point 1, 0. But I'm going to only look at the line segment where z runs from minus h to h. So obviously, if you rotate this about the z-axis, you are going to get a cylinder. Okay, and the volume of the cylinder is very easy to calculate. Now, what happens if you tilt the line segment slightly? As follows. By this, what I mean is that I look at the plane that is parallel to the YZ plane. So previously my line segment was here. I'm going to push it off by a slight angle so that it lies still in the plane that is parallel to the YZ plane, but it's now tilted slightly at an angle. So specifically, the equation of this is going to be x equals r. So the x is still going to be constant, but instead of y equals to a constant, I have y equals to az. So this has a slope to it now. And same thing, I'm going to look from z ranging from minus h to h. So make sure you understand how this line segment looks like. Okay, so once again, this is the perspective. If you view down the x-axis, it's not, the line segment does not cut through the origin, but it is on the plane that is parallel to the YZ plane. Okay, so this time, if we were to rotate this line segment about the z-axis, what do we get? So here's an easy way to think about it. We can think about each point on the plane generating a circle. This point, right at the extreme of the line segment, is of a certain distance away from the z-axis and it generates a circle. The point that is at 1, 0, 0, or rather r0, 0, is of distance r from the z-axis and it will generate a circle of radius r. Now, the point that is at the end is further away from the z-axis, right? Because after all, it not only has a x coordinate of r, it also has a y coordinate that is positive, right? Whereas here at the center, it's just x coordinate of r, y coordinate is 0. So this is of a further distance from the z-axis. So when you rotate it, you get a bigger circle. And as you move closer to the midpoint, you get smaller and smaller circles, which explain why you get this curved-looking cylinder. So you might see where we are going with this, but let us first calculate the volume of this curved cylinder that is generated under the general parameters R, A, and H over here, because then later we can just plug in the values for our use case. So to calculate a volume is actually quite straightforward. We will slice this volume into layers of disk. So at height h, the stick, as I mentioned, is at x coordinate r and y coordinate az, which means the radius of the disk is square root of r squared plus az squared. So the volume of the disk at height h of a thickness dz is actually pi times r squared, which is, or rather radius squared, which is r squared plus a squared z squared times the thickness dz. So to find the volume of solid, all we need to do is then integrate this over z ranging from minus h to h, which you can do very easily because this is with respect to z, so I just create a z here, and this is just 1/3 z cubed. So I have this expression, I plug in minus h to h, and I have this a bit slightly complicated looking expression here, but do not worry, it will massively simplify later. So here is the volume of solid under general R, A, and H. Pretty interesting that this is even tractable. So a good start. So now we pull our various diagrams together and see how we can approach this middle section. So this middle section consists of basically all these edges, these 6 edges zigzagging along between the blue triangle and the purple triangle. So we have this zigzag pattern going on, and each of these is actually, I'm going to claim, of this scenario over here, or this scenario, they are the same diagram. So if we can show this and find what is the values of the A, R, and H in this scenario, we will be able to plug in and find the volume. So how do I convince you that this line segment is of this scenario? So what I need to do is I need to find the equivalent of the plane parallel to the YZ axis and then show that I just rotated it, the line segment slightly. So here is how we can do this thought experiment. So to convince you of this, let us look at the line segment EF as a specific example. So EF over here. Now this diagram has no axis shown here because it's drawn in a different orientation. So just imagine that we have the point E and the point F here. These are the coordinates. And I can tell you what is the coordinates of the point M, the midpoint of EF. Now, if I very randomly create this point 1.512, you will notice that this is of a displacement of 111 away from M. So over here, I have a vector drawing from M to the blue point, and it is 111. So now if I consider the plane that is spanned by this vector and this line, remember two lines that are that are intersecting like this will describe a plane. So I have a plane that is containing this and this. And guess what? This vector 1, 1, 1 is parallel to our rotation axis. So remember, our rotation axis is in the direction 1, 1, 1. So this is exactly the same setup now as our scenario over here. We do have a plane which is previously what we call parallel to the YZ plane. We have our axis, then our line segment initially started off vertically, so to speak, which is along the axis, but we tilt it along that plane that was parallel to the YZ plane. Yeah, so you see it's exactly the same scenario here. And once we have this dictionary to help us translate from our special case to the known scenario, we can now try and figure out what is the values of R, A, and H. So I just go put the volume of solid here to remind us, but we first need to find the values of R, A, and H. So let's begin with the value of R. So R, as you recall, is the distance of the middle of the line segment to the rotation axis. So this is, in this case, finding the perpendicular distance of M to the axis, which thankfully is very easy because it is also basically us finding the distance from M to the middle of the cube. Why middle of cube? So basically, the perpendicular fit from the midpoint to the axis is going to be the midpoint of this axis segment over here. So you can see by symmetry considerations, the midpoint projected down the axis is basically the sort of middle of the rotation axis, and in our case, it is the middle of the cube. So the fit of the perpendicular is at 0.5, 0.5, 0.5, which then tells us we can directly calculate the vector MQ, which is this vector minus this vector. And what we have is then MQ is of length 1 over square root 2. So R is 1 over square root 2. Now we need to find the value of H. Okay, to find the value of H, which is basically what is the value of H is, I need to describe the height here, right? So remember previously the height was from minus H to H. And to get this height, I need to basically take the projection of F onto this thin arrow over here. Okay, remember over here in this diagram, for example, I have the plane parallel to the YZ plane. Then if I project it towards here, I get the height. So similarly, I need to project F perpendicularly onto the thin arrow here. So I will let P, the red point, be the fit of the perpendicular from F to the thin arrow. Okay, now this is a pretty standard vector stuff. I need to find the coordinate of this fit. And to do this, notice that because P lies on this line, the thin arrow, so it has general coordinates M plus C times 111 for a specific C. Correct? All the points on this line is M plus some scale multiple of 111. And since FP is perpendicular to the thin arrow, this tells me that FP dot 111 equals 0. And to find FP very easy, FP is just the coordinate here minus the coordinate for F. Okay, so FP dot 111 equals 0. If I expand out this dot product, I'll get minus 0.5 plus C plus C plus C equals 0. So C equals to 1/6. So if I plug 1/6 back here, actually I don't need to. All I need to know is that this vertical distance here is C times 111. So the vertical distance, aka our height, is the length of 16111, which is square root 3 over 6. Okay, doing well, doing well. We are almost there. So now lastly, we need to find A. To find A, what we're going to do is we observe that previously A is basically the slope, but or rather the reciprocal of slope, but the other way we can find A is by taking ratio. So we can take the ratio of this length over this to get a, because for every 1 unit that z increases, y increases by a. So if we can find the length of fp and divide by pm, we'll basically get the value of a. And thankfully, we can already find out what's the length of fp, because fp, we just plug in the c that we found previously, and we have this is the expression for vector fp, so the length fp is just 1 over square root 6. And so if we take, as I mentioned, the ratio of fp to the vertical height, we actually get a, which is square root 2 in this case. So here's the grand finale. So I'm going to plug in all the values r, h, and a into this formula for the volume of the middle. And it looks a little bit ugly at first, but if you simplify the substitutions, you get this, which simplifies further to 5 pi over 9 square root 3. And voila, this middle chunk has volume 5 pi over 9 square root 3. And you see, this actually adds up very nicely. 295929 equals 1. So we do have the final total volume is just pi over square root 3. Bet you didn't see that coming. This is really elegant number in the end. Wow, this is actually quite a journey, and I hope you enjoy this problem. I certainly didn't think it was possible to find the volume at the beginning, but it's actually not as complicated. It could have been much worse, right? So just simple calculus, vector geometry, and the final answer is quite elegant. So I hope you enjoyed this video. Let me know in the comment section what you think, and I will see you in the next video.